Pure versus mixed. Quantum state showdown inside the Bloch sphere. Explore the geometric interpretation of quantum states and learn how the Bloch's vector's length reveals whether a state is pure or mixed. Here's one of the most fascinating things that I've seen in this book, and it's the Bloch sphere, and it comes into play quite a bit in a lot of different applications, which we'll talk about soon. So, this problem 12.8, the last of the book, the last of the chapter, wants us to show that the most general density matrix for a spin-1/2 particle can be written in terms of three real numbers, A1, A2, A3, with the density matrix given here with all the various components, and we could write this as 1/2 then times 1 plus A dot sigma, which are the Pauli matrices, as stated here. Hint, it has to be Hermitian and its trace must be 1. Then B, in the literature, A is known as the Bloch vector. Show that rho represents a pure state if and only if the magnitude of A equals 1, and for a mixed state, magnitude A is less than 1. Hint, use problem 12.6c, thus every density matrix for a spin-1/2 particle corresponds to a point in the Bloch sphere, so darn cool, of radius 1. Points on the surface are pure states and points on the inside are mixed states. C. What is the probability of a measurement of SZ would return the value of positive h bar over 2 if the tip of the Bloch vector is at the North Pole, the center of the sphere, and the South Pole? D. Find the spinor chi representation of pure states of the system if the Bloch vector lies on the equator at the azimuthal angle phi. Okay, so why do we care about all this? Well, the Bloch sphere is an important thing because it provides a geometric representation of quantum states for two-level systems, such as spin-1/2 particles. The visualization allows for intuitive understanding of pure and mixed states, as we see from Part B, easy representation of quantum superpositions, and simplified calculation measurements of probabilities. The applications of this, however, are a little more nuanced because the intuitive representation of single qubit operations, geometric interpretations of quantum gates, and visualizations of qubit evolution during quantum algorithms, which is where this application actually came from a paper, which is where I got the original image from, which will be linked in the description if you want to check it out. Very interesting how they actually utilize it. Of course, within looking at a couple of these papers, the big problem comes in the challenge of this is, what about multi-systems? Because although this is a two-state system, it's a single qubit system. What about multiple systems? That's where it can be troublesome. Now, of course, there is a lot in this particular question. Although most of it's in the video, the PDF puts it together in a little better way of flowing, especially with some of the algebra in between. So if you want that, feel free to access it using the Patreon link in the description, or comment and I'll send you the link directly to this post. Either way, we'll find a way that works. Before we jump into today's topic, you should know that my goal is to break down these complex physics concepts using exercises from top books. If that sounds like something you'd enjoy, hit subscribe and join us in exploring the universe. Now let's dive into this Bloch sphere. Okay, so stop number one, we have to be careful to start because in the most general sense, the density matrix for a spin-1/2 state is a 2x2 matrix which can be written as rho with 4 components, all part of some complex number. So they're not necessarily uh, real or purely imaginary, but some combination. Okay, but we know that from rho having to be Hermitian, which we referenced in equation 12.3 and was given in the hint, or problem 12.6a, we know that C1 and C4, in order to be Hermitian, need to be real because they have to be equal to their conjugates. Okay, that's pretty cool. But speaking of conjugates, this also tells us that C2 and C3 need to be conjugates of each other. So it doesn't really matter which one we put as B2 plus IB3 or minus, they just have to be conjugates of each other. And now from here, we see that they're all real numbers. So now we're getting honing in to exactly what we want for this formalism. We also know that for a density matrix, for any density matrix, the trace must be 1. Okay, so if we add this up on the main diagonal, B1 plus B4 has to equal 1. Therefore, we can substitute B4 in terms of B1 into it. And that's how we simplify that. And through another series of substitutions, just form matching really, what we can do is see that if we let B1 equal this, B2 equal that, and B3 equal this, then we get this form here, which is very close to what we want. Notice how everything's over 2, so we can factor that out in each component. Easy enough. Once we do that, we see this 1 and 2, or this 2, this 1 goes to a 2 if we're factoring out a 1/2, and then this red one minus this blue, minus this 1 here that's crossed out in blue returns to a 1. But because every single component has a 1/2, we can factor out of the matrix as a whole and get to the equation 12.38, which is what we were trying to do. Now from here, we have another trick up our sleeves that makes this incredibly more compact. So starting from this and doing a rebatch on the color code, where we see we have constants in purple, the A1 terms, A2 terms, A3 terms, all in separate colors, we can linearly separate this into constituent parts. So purple, blue, reds, and greens all separated out. We see that we have this just turns into the identity. We can factor out an A1 component here to both, A2, A3. And what we notice about these is this is a poly matrix. You have the poly matrix on blue for X, Y, and Z, Y, and Z. And if we rewrite this down here, we have A1 sigma X, A2 sigma Y, A3 sigma Z. And guess what? That is a dot product representation of two vectors. So we have A dot sigma, and we had just shown that we can write this density matrix for a spin 1/2 system in terms of this generalized density matrix, or as a dot product of the Bloch vector with the poly matrices. That is extremely fascinating. I don't know how they recognize this, but I guess back in chapter 4 when they alluded to it and how these matrices, the poly matrices with their traceless properties added up, this came out to such a huge thing. It's truly remarkable. So, with that being said, outside of me having a little nerd rant, what do you think about this? Drop a comment below with your thoughts because this is really fascinating. Now we get on to part 2. And this is the trace property, right? So, using the results of 12.6c, we can calculate the trace and compare what would be true for a pure state versus non-pure state. So if we know that the trace here, which we argued about in 12.6 and I think again in 12.7 briefly, we see that the trace squared of the density squared is just two different states being squared. So we need to color code them green and blue. Um, Technically, you could re-index these and just have something different, but it's kind of beyond what we're trying to show here. That being said, we have 1/2, that goes to 1/4, and then we have the matrix multiplication shown here. I think at this point you know how to do that, but got to put it in. Simplify. Instead of distributing everything, we see that we have a plus here and a minus here for two sets of these matrix components. So I just canceled them out, and then that simplified our algebra here. Now from here, we still have to find the trace of this, which is just the main diagonal term. So let's add them together. When we add them together, we have a plus here, a minus here, so they cancel. Outside of that, you have a duplicate of the same thing, so you have 2 here. That 2 reduces that 4 to 2, and then we just have 1/2 equals 1 plus A dot A, which is magnitude A squared, exactly what we want. And since we know that this has to be less than or equal to unity, or 1, via the problem 12.6c, we know that for any valid density matrix, this inequality must hold, okay? And as a result, what we see in solving this thing is pretty easy. You just multiply by 2 minus the 1, and then we see that the magnitude A squared has to be less than or equal to 1. Take the square root, then we're fine since both are positive. And in this case, equality only holds if and only if the states are identical, okay? Otherwise, we're definitely less than 1. That's a property of inner products, which is in the appendix. So consequently, for mixed states, non-pure states, the magnitude has to be less than 1. And that's pretty remarkable, actually. Very cute formalism, all things considered. But nonetheless, this is the introduction to the Bloch vector and Bloch sphere and how they can have representations geometrically of the state combinations. Pretty darn cool. Now on to stop 3 with probabilities. So to calculate the probability of SC yielding H bar over 2 positive, we employ a strategic approach. We start with the principle that the expectation value equals the sum of each eigenvalue multiplied by the probability, which is what we see here. Positive, 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 negative, negative. But in the note here, we know that the sum of the probabilities has to equal 1. So from doing that, we can solve for p negative in terms of p positive, and that's what we do here to substitute in. Now, since we know what we're looking for with both the eigenvalues, positive, negative, h bar over 2, we could factor them out. And then we just have some algebra to clean up here. And ultimately, what this gives us is, if we want the probability of this thing given the results, we could solve this for the expectation value in terms of the probability, which is what we did here. Simplify that down, and we see that the probability for positive is the expectation value of SC over h bar plus 1/2. The reason why we do this is because this gives us the probability of measuring spin up along the z-axis, where we know how to find the expectation value SZ from the density matrix itself, and that's pretty darn helpful. So, the density matrix, from the density matrix perspective, we can get the expectation value by the trace as shown from equation 12.33, where we have the density matrix and the operator itself. The operator here, once we plug in the general form, the operator came from chapter 4 back in the spin state, so it's 4.145. Easy enough. H bar over 2, 1/2, multiply to h bar over 4. Distribute, be careful this negative here, but you see what's going on here. Trace some of the diagonal. We see that this goes there. Easy enough. We see that this 1 and -1 cancel. We have a duplicate of A3, which is the block vector component. So we're pretty good there, which is really what we want. We simplify this down to one block vector component for SZ. Makes sense that A3 is the Z component, so it's all coming together, which is, again, remarkable how well it's working. I would not have suspected that, but somebody else did, and it revolutionized a lot. So that being said, we have 2 of these, so that 4 reduces to 2, shown in red. So we see what the expectation value is. Plugging that into the probability equation we found, the h bar cancel, leaving you with A3 over 2, so factor out of 1/2, and thus leaving you with A3 plus 1. Okay, so that's pretty darn cool. And so for the given directions that we were given, where we were at the North Pole 0, 0, 1, we plug that in and we get a 1. So that geometrically makes sense. If I want the spin up in the z direction and I'm at the North Pole, of course I'm going to find a spin up eigenvalue. That makes sense. Perfectly fine. Now, if I'm at the center, I could be in between spin up, spin down, so I'll be there about 50% of the time, and that's exactly what we get by plugging it in. Now, of course, if I'm at the South Pole, which is this block vector here, I'm never going to find a spin up there because I'm always at the South Pole. So intuitively, these make a whole lot of sense, and it was pretty easy to find all these probabilities, all things considered. So probability is not too bad so long as you systematize it from the eigenvalue perspective, then use the density matrix to calculate the trace. That was very easy to do, all things considered, once we found the general form. So if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. Now let's wrap this problem up with part D. So in part D, a point in the equator of the xy plane with the azimuthal angle phi yields the Bloch vector, which we can get from the general form or plug into the general form as we see here. A is equal to 3 components. We know that we're in the xy plane, so z has to be 0. And we see that from the azimuthal angle, we have some component, again, because we're normalized unit vector or unit sphere style. So we have cosine for the x, sine for the y, which I think, again, was pictured. I'll have to double check, but nonetheless, you've seen something like this before. So plugging these components in by reading off into the general form for spin 1/2 density matrix, we see that we end up with this. Note that, again, in the main diagonal terms, we just end up with 1. But now we have cosine phi minus I sine phi, cosine plus I sine. Euler's identity comes in again, and we see that we get exponentials. That's pretty darn cool. Okay. And now a little note, of course, if you've taken linear algebra, you can kind of see that with these being, what they are, we have eigenvector, eigenvector here. Pretty darn cool, and we see that that will come up again here shortly. So for a spinor of the form chi equal AB, the density matrix as per equation 12.28 is given by the summation of the chi vectors with their probabilities. Okay, so since we're going from 1 to 1 and we're just trying to get a general spinor for the state, we know that the probability has to be 1. So that's easy. And then we see that says 𝐸1, easy enough, which we just reduced down to chi and chi, which of course can be represented from the ket vector chi and the dagger there, easy enough. So if we plug in the general form A conjugate transpose through the multiplication, we see what we get here. We get the magnitude squared, and then of course be careful on which one's conjugate. All right, no big deal there. Now comparing this with the general form that we had just had, we see that magnitude A squared equals 1, and so does magnitude B squared. And also our off diagonal elements are negative I e to the negative I phi, which is the conjugate, double conjugate of this, um, or A star B, that should be switched there, excuse me, this should go there, or A star B equals e to the I phi. So there's two possible routes due to which one of these actually equals 1. Okay, because it's ambiguous which one it is. So let's take it case by case. So if A equals 1 because the magnitude equals 1, then we plug in 1 star B, which just gives us B. Therefore, we see B equals the positive I phi. This gives us the chi1 here. And then if B equals 1, then A conjugate on the B, this gives us A equal e to the negative I phi vector here. But notice that this was column vector 1 in that matrix and column vector 2 in that matrix with the normalization factors AB. Pretty darn cool. You know, we can kind of see the writing on the walls after you stare at it enough. That being said, finding the normalization, set the inner product equal to 1 and roll through. Again, I just did this to be complete, but you can kind of see once you take the conjugate transpose, you get magnitude here, row vector, column vector, multiply them out. You know, the exponentials cancel as expected, you get 1. So you get 2 times the magnitude A. That tells you have A equals 1 over root 2. Nothing new, you've seen that 1,000 times by now. Run the same thing for B, and you see that B gives you 1 over root 2 as well. Just be careful with your positive, negative, where your exponentials are, things like that, and you'll be good to go. So the possible spinors up to arbitrary phase are given as chi1, chi2, both same normalizations. The column vector 1, column vector 2, or the eigenvectors, however you want to perceive them. Either way, you're good to go from this. And that is a very quick tutorial on things that we already kind of knew, but were summarized so concisely and succinctly with this Bloch vector and Bloch sphere notation. So darn cool. So that was a really fascinating video, and if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful for each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.